Hi, so today we're going to talk about what the limit definition of a derivative is. We're going to actually start getting into real calculus and talking about derivatives and all that fun stuff, the basis of what the rest of your calculus class is going to be about. Okay, so let's get started. So what is a derivative and why do we need to know about it? So a derivative is a function that tells you the rate of change of something, and that's why it's really important. Derivatives help us to further analyze functions. We can talk about increasing and decreasing intervals of functions, how fast a function is changing. Derivatives become really important when we start talking about position, velocity, and acceleration functions and all that great stuff. And before we actually start out taking derivatives with certain derivative rules, we start off with a limit definition of a derivative. So we use that limit process that you guys have been working on for probably a few weeks to find a derivative. So the first thing you need to know for finding a derivative using this limit process is what a difference quotient is. And what the difference quotient is you might have seen this in pre-calculus. It's f of x plus delta x minus f of x all over delta x. So what delta x stands for is a small change in x. So when we talk about delta x, it could be something like 0.1, 0.01, 0.00001, a very small change in x. So the difference quotient is really just some function where you evaluate x plus some small change in x, you subtract out the original function and divide by the change in x. And to find a derivative using this, all we do is take the limit of it. So our derivative, which we use the notation f prime of x, all that's going to be is the limit as delta x goes to 0 of the difference quotient. So f of x plus delta x minus f of x all over delta x. So you're going to have to use all of those limit techniques that you've been learning for the past few weeks in order to do this. So the difference quotient and this limit definition are definitely something that you want to have memorized. It's really going to help you for quizzes and tests, and it should be something that's stuck in your head at all times. So let's actually take a few limits and see how this works. So the first example problem that we're going to do is find the derivative of f of x equaling x squared plus 2x. So the first thing that I like to do is find out what the first part of my difference quotient is. I like to figure out what f of x plus delta x is. And I like to do all my simplification before I actually plug into the limit, so it's a little easier for me to see what I'm handling once I want to go and take that limit. So to find f of x plus delta x, what you're going to do is you're going to plug this x plus delta x in for everywhere you see an x in your function. So what this is going to turn into is x plus delta x squared, the whole quantity squared, plus 2 times x plus delta x. So now we're going to do some simple algebra and simplify this so we don't have anything inside of parentheses. So when we square out a binomial, it's really important to remember that that's not just going to be x squared plus delta x squared. We got to remember to FOIL out the binomial. So we'll write out what that is. And then we can distribute our 2 through. So we get plus 2x plus 2 delta x. Okay, so now let's FOIL together these first two quantities. So we're going to get x times x, so we're going to get x squared plus delta x times x, delta x. So we get plus delta x squared. And then we got to do our middle terms too. So we're going to get x plus delta x plus another x plus delta x times delta x rather. So plus 2x times delta x. Just wrote them in the wrong order. Excuse that. So then we get plus 2x plus 2 delta x there on the end. Okay, so this whole thing is going to be our f of x plus delta x. So now that we know that, we can plug into our limit definition of the derivative. So we get that the f prime of x, the derivative of x, is equal to the limit as delta x approaches 0. And we're going to write our formula just so that we can make sure that we remember it. So we get f of x plus delta x minus f of x all divided by delta x. Okay, so let's start plugging in for what we know. So we have the limit. Always really important to continue to write your limit down in front of it so you remember what you're doing. And now we're going to plug in for this thing. So we're going to get x squared plus 2x delta x plus delta x squared plus 2x plus 2 delta x. I just reordered a couple of the terms. Minus, and now we're going to plug in f of x. Now, it's really important whenever you plug in f of x that you put parentheses around it. So really, let's just put parentheses back up in our formula. So now we get minus parentheses of x squared plus 2x. And all this is going over delta x. So you might have noticed before that since we're taking the limit as delta x goes to 0, we can't just instantly plug in 0 and take our limit because we have a 0 in the denominator, so things aren't going to be working out so well. So what we need to do now is clean up that top, our numerator of our fraction, because we probably have some things that are going to cancel, and you want things to cancel because then the limit's going to work out very nicely for you. So again, we're going to write our limit. Delta x goes to 0, and we're smart people, so we're not going to rewrite the whole line. We're just going to show that we have to simplify, we have to distribute this negative sign. So this is, if we make this a positive, it's going to be negative x squared and really a negative 2x. We'll just cross off that plus sign. That way we don't have to rewrite the whole thing. So we can see that we have a negative x squared here in the back and one in the front. So our positive x squared out here is going to cancel with this one. And then we have a positive 2x in the middle, which is going to cancel with this negative 2x there in the end. So what we're left with is going to be 2x delta x plus delta x squared plus 2 delta x all over delta x. Much nicer only having 3 terms there in the numerator. Extend our page there. So you might have noticed that every single term in the numerator has delta x in it, which means I can factor out a greatest common factor of delta x. So if I factor out a delta x now, I get 2x plus delta x plus 2 all over delta x. And now that I have my delta x factored out of my numerator, I can cancel it with the one that's in the denominator. So now our limit just turns into, the limit as delta x goes to 0, of 2x plus delta x plus 2. So if now we can plug in 0 for delta x because we don't have anything in our denominator. Nothing's going to be 0 over 0. What we're left with is 2x plus 2. So that means that for the function x squared plus 2x, our derivative f prime of x is equal to 2x plus 2. Okay, so now what would you do with that? What you could do with that is you could plug in x values and find the rate of change of your function f of x at any of those x values. Or in other words, you could find the slope of the curve at any point on the curve, which is a really nice thing for derivatives. So let's do one more example. Make it a little harder. Let's throw in a rational function. Let's find the derivative of f of x equaling 1 over x. So again, we're going to first find that first part of our difference quotient. And this one's really easy because we don't have any weird terms. We're just going to put 1 over x plus delta x. No simplifying required, so we're good to go. So now we're going to start into our derivative. So f prime of x equals the limit as delta x goes to 0 of 1 over x plus delta x minus, throw in our parentheses, 1 over x all over delta x. I know I didn't write the formula this time, but if you forget, it's just going to be right over here then. Just write it real tiny. That's just the limit as delta x goes to 0 of f of x plus delta x minus f of x, running out of room, all over delta x. Okay, so now we have complex fractions. As mathematicians, we don't like complex fractions, so let's get rid of them so we can take our limit. So we have the limit as delta x approaches 0. Okay, so now how do we want to get rid of these complex fractions? So why don't we multiply in by something into the numerator and into the denominator in order to cancel with our two little numerators in here. So, I'm sorry, little denominators. So our little denominators are x plus delta x and x. So that means if we multiply in by x times x plus delta x, we'll cancel with both of them, which is exactly what we want to do. Okay, so let's multiply in now and see what we get. So we multiply into this fraction, we get that our x plus delta x's, they're going to cancel. So all we're going to be left with in the first term is x minus, make sure we keep our parentheses there. Now if we distribute it to the second term in the numerator, our x's are going to cancel, and we're going to be left with x plus delta x. And then we don't even have to simplify anything in our denominator. We're just going to leave it as x times delta x, all times x plus delta x. Normally you don't want to distribute into your denominator because it makes things a little harder to see if they cancel. So again, we're going to distribute our negative term right here. So this is going to make this a plus, minus, minus. Let's see what cancels. So now we have a positive x here and a negative x here. Those are going to cancel. So all we're going to be left with is the limit as delta x approaches 0 of negative delta x all over x times delta x. Should probably put in the multiplication sign there. And then times x plus delta x. So now we have a delta x left in the top and a delta x in the bottom. So we can cancel them out since it's just multiplication. Rewrite what we have, and then we can take our limit. So we have the limit as delta x approaches 0 of negative 1 over x times x plus delta x. So now if we plug in that 0 for delta x and take our limit, we get negative 1 over x times x plus 0, which is just going to be negative 1 over x times x, or x squared. So for the function f of x equaling 1 over x, your derivative there, f prime, is just going to be negative 1 over x squared. So that's how you go about taking a derivative using that limit taking process. You take the limit as delta x goes to 0 of your difference quotient. So the next video for this section in your textbook is going to talk about how to actually use this derivative to get something that's useful for us. We're going to find the limit. We're going to find the derivative of a function and then use that derivative to help us find the equation of a tangent line at a point on the curve. So thank you so much for watching. Have a great rest of your day.